Hello everyone. Here today I will talk about machine learning inferences on the edge. That's specifically actually neural networks serving on edge devices. So here is the rough agenda. Firstly, why we want to run machine learning inferences on the edge and how to infer on that. Then what kind of common issues we find on the edge devices to resolve. And then how about our solutions? Lastly, if we have some time, we can do some POC demo. So firstly, about why we want to run machine learning inferences on the edge. Here we talk about edge devices specifically. Machine learning is pretty hot recently in different industries. And actually, for most of machine learning or also the deep learning um, algorithms, which is mostly relative to neural networks, to get that model, we really requires a lot of data, big data, from different data sources, like things in the Internet of Things, like from many peoples, and it's also possible to get some data from cloud, from application running on the cloud. So with all this data, the trainings mostly happen in the cloud because there are enough resources and enough computing hardwares to run on these trainings globally. But if the customers want to make certain decisions and take actions in their production environment, they generally expect to run all these inferences on the devices, which is pretty near to the data sources, to the things, to the sensors, to the actuators. With that, they can achieve much less latency and they can achieve less dependency on the communication networks, which generally means the connection from the edge devices to the cloud. And they can achieve much more scalability, considering that all these inference tasks are running on different physical boxes. And there are maybe other considerations for that decision to run inference on the edge devices. So how to run the inferences on the edge? Because machine learning inferences are kind of basically floating point computation in matrix. That's kind of um, arithmetic algorithms running in the devices. A lot of floating data computing within matrix operations. But generally, CPUs are not designed to run these kind of floating operations in matrix. CPUs are good at uh, integer computing and operations of command instructions. But compared to GPU, FPGA, VPU, XPU, TPU, ASICs, they are not so good for that. And on the other hand, CPUs in edge devices have to run multiple tasks in parallel. They have to handle the communication, handle the things operations at the same time. Although there are multiple cores, but the resources expected for inferences are quite high. So in a case, multiple leading vendors create some, we call it a heterogeneous system architecture to meet the requirement. They produce some hardware accelerators for edge devices to run all these inferences, such as embedded GPU, or VPU, or edge TPU, or FPGA, ASICs around that. And to supporting all these hardware accelerators on edge devices, special SDKs or toolkits are created by the vendors and leveraged to run the machine learning inferences on the edge devices. The mechanisms are kind of similar. So in general, firstly, optimize all these neural network data models trained in the cloud, and the smaller or trimmed down data models will be executed in the edge devices on the heterogeneous accelerators with some light toolkits compared to the full frameworks in the cloud. And optionally, some technical stack. In some technical stack, some compilers also leverage to compare models to native code on the accelerators to improve the performance a little bit more. Let me show you some examples. So here is a web page from Intel. You can see that there is a toolkit called OpenVINO to run all these uh, inferences on the edge. There are clear steps to run the model optimizer and the inference engine. They depends on certain different hardware here listed already. Like in NVIDIA, this is page on NVIDIA TensorRT, which is to run inference accelerators. From their architecture, you can see clearly that they have the trained model, they want to optimize, tune that model, and afterwards, the model will be inferred on the hardware embedded GPU produced. Um, like Xilinx, FPG leading vendor, they have the AI edge platform. And from the architecture, you can see clearly that they have heterogeneous hardwares on the board and compile different runtimes and module pruning and optimization and quantize toolkit to shrink the models into the smaller situation. And some others like Google Edge TPU, they also have a framework uh, uh, called TensorFlow Lite, and they leverage the Edge TPU to run all these trimmed model in edge devices. The hardware will run some special code for that purpose. This is TensorFlow Lite. That's actually could be same part of TensorFlow framework, but specially designed for mobile and IoT devices. Okay, get back to our deck. Uh, so with all these different accelerators and SDKs, what kind of issues are left to resolve? We found that for all these different technical stack, applications is actually tightly coupled with hardware accelerators and SDKs. You may find that from their code, they have to call the special SDK APIs in that technical stack. And in a way, hardware and software bundles of edge devices are generally provided by the vendors with a kind of preferred clouds together for the customers. So generally, that's the only choice. That's kind of easy to understand because the neural network models and the relative applications are generally seen as a bundle together. So for application, that's also relative to certain clouds. And with all that, the migration risks and the efforts are inhibiting. You can clearly get that point. So with all this, on the other hand, computing performances are variant from benchmarks. You can see that their hardware architectures are different, although there are some common features are available, like seemed single instruction multiple data, like the core frequency is also very important to get performance, like the computing unit numbers and the onboard, on-device memory, and the actual architecture for that accelerators are quite relative to uh, the theoretic benchmarks. The actual application code is also quite important to get the best performance from hardware and SDKs. With different code from developers, we can get pretty much, quite different result with the same hardware SDK. So how customers have to choose all these hardwares? If they choose one hardware and implement the code together with the SDK, they are really not easy to switch to another stack with that hardware. So users are locked in by the vendor literally. So that's the common issue we found with all these situations. What's our solution? VMware is not a hardware vendor. We will not create another hardware accelerator for machine learning inference on the edge. What we want to do is trying to create abstract layer to decouple the software and hardware, decouple the edge from cloud. We want to create a common machine learning inference interfaces with the REST API people are generally familiar with. And we want to support multiple hardware accelerators and SDKs to be hardware vendor neutral. And we want to release all this relative code into an open source community for the inference interfaces and our reference implementation, so as to build a vendor neutral and open community for machine learning inferences on the edge. So every users have the flexibility to choose whatever software and hardware and whatever cloud they want to choose for machine learning training and inferences on the edge. And finally, we want to integrate that part with the open and neutral edge computing application frameworks. For example, Azure Foundry, managed by Linux Foundation Edge Umbrella, to achieve that goal at a big picture. Thank you very much for today. You're watching. Bye.